Hi, everyone. Welcome to another Neural event. We are very excited to have all of you join us. So just as a start, we are the Neural Engineering Research Venture, and our aim is to bring neuroscience to life in Africa and around the world. And we are myself, and I will, sorry, I'm just quickly going to sort out the sound here. Perfect. So we are myself, and I will be hosting with Siobhan this evening. And then Darby, you can look out for in the comments. So we have a couple of exciting announcements. And the first of this is the Launchpad or the Neuro Launchpad announcement. So if you are a grad student or a postdoc who is interested in presenting your work to a large neuroscience audience, then you can check out Neuro Launchpad. This is a virtual seminar series that is designed to give exposure to trainees. And this will run from October to December of 2020 with 2 20-minute talks a week. And they are already accepting submissions. So if you're interested, definitely check this out. Then secondly, there's another NeuroMatch conference coming up from the 26th to the 31st of October. And this time around, it'll be a super conference. So it is not limited to computational neuroscience, but it includes the entire spectrum of computational, developmental, social, clinical, cellular and molecular, motor, sensory, education, ethics, animal, and human neuroscience. Okay, so then next up, we have Worldwide Neuro. That is a platform for sharing a varied collection of neuroscience talks and seminars, and it's all conveniently located in one place. So definitely go check this out, and all the talks are also added daily. Then we have ABC, which is a AI, brains, and computational thinking meetup group based in Cape Town. And this is focusing on natural and artificial intelligence, how they differ, how they are alike, what they can learn from each other, and how we can learn to harness them, and why it is important to study all of these fields. So definitely also check this out. Then just a couple of house rules. Please remember to use respectful and inclusive language. So we have the Ask a Question feature at the bottom of the screen as well. So throughout our presentation this evening, remember to post your questions, and also remember to vote for your favorite questions. And after the presentation, we will have a Q&A session where the most popular questions are most likely to be asked first. And we will also invite you on screen to ask your questions live. If you don't have a mic, don't worry about it. Please just remember to add please ask to your question, and then we will ask on your behalf. And then also, if your connection is slow, just try to refresh your browser. This usually does work. And if your connection fails, don't worry about it. The talk will be available to stream after the event as well. Now I will hand over to Siobhan, who will be introducing our speaker for the evening.
Thanks, Julianne. I'm very excited to welcome our esteemed speaker tonight, Professor Michelle Johnson, who is currently a tenured associate professor of physical medicine and rehabilitation at the University of Pennsylvania. She has the secondary appointment as an associate professor in bioengineering and is a member of the Mechanical Engineering and Applied Mechanics graduate group. She has a Bachelor's of Science in Mechanical Engineering and Applied Mechanics from the University of Pennsylvania and a PhD in Mechanical Engineering with an emphasis in mechatronics, robotics, and design from Stanford University. Professor Johnson completed an NSF NATO postdoctoral fellowship at the Advanced Robotics Technology and Systems Laboratory in Italy. Professor Johnson directs the Rehabilitation, Robotic Research and Design Laboratory located at the Pennsylvania Institute of Rehabilitation Medicine at the University of Pennsylvania, specifically at the School of Medicine. This lab is also affiliated with the General Robotics Automated Sensing Perception Lab. Professor Johnson's lab specializes in the design, development, and therapeutic use of novel, affordable, intelligent robotic assistants for rehabilitation in high and low resource environments. The emphasis is on using robotics and sensors to quantify upper limb motor function in adults and children with brain injury or those who are at risk for brain injury. And on top of all of that, she is also a US Fulbright Scholar. So thank you very much for joining us this evening. And we will now hand over to you to start the talk.
Thank you so much. So is that me?
Okay, Professor Johnson, we can't hear you at the moment. I think you might have muted your mic. Siobhan, you can also not hear her.
No.
Okay.
There was the extra mic that was added that I'm thinking is maybe just being switched off at this point.
Yeah, it might be. I'm trying to toggle the mic on. No, we still can't hear, unfortunately.
Should we maybe re-invite Professor Johnson to start the process again? Yeah, it might just need a reset.
I think that's a good idea. Yeah,
Off
so
and
I'm
on.
quickly going to reinvite you. Cool. Perfect. Okay, she should be joining again momentarily.
Can you hear me?
It's
like it's weird. Can you hear me?
Yes.
Yes.
Now it's working.
And no echo.
Can you hear me or no? I can't hear you. Wait, hold on. I'm having a bit of feedback. I think that's my issue.
Yeah.
I can hear you, but I'm having major feedback. So I'm hearing myself echo. I apologize. I'm trying.
We don't hear the echo.
Technical difficulties, always there.
Yeah.
I'm going to plug out this extra mic and I'm going to see if that solves the problem. If not, we may have to re-invite me again. I apologize again.
No problem.
Okay. Yeah, this doesn't seem to be working. So I think I'm going to quickly re-invite you again then. Okay. I didn't hear the feedback the second time around though.
No. It might also help to mute ourselves if there's feedback, but
yes.
To say she's hearing.
Yeah.
Okay, can you hear me? So the echo is there, so I'm not sure if it's me. All right, I'm going to go ahead and share screen. Okay.
Do you perhaps have earphones or anything like that? That normally helps with the
feedback.
feedback.
I figured out what was going on. I had an extra web thing open, so I was getting the perpetual feedback. We're ready.
Okay, fantastic.
Apologize, everyone. Yeah.
No problem.
Okay, ready. I'm sharing my screen now.
Perfect.
All right.
Yeah, we see. Okay. That's awesome.
Perfect. Okay.
Great.
So thank you so much for the invitation and for allowing me to be able to speak with you today. I have the pleasure of just kind of talking a little bit about our work in Affordable Robots computer systems to identify, assess, and treat impairment after brain injury. I'm going to kind of talk a little bit about our rationale, give you a little bit more about background on what we do. And I'm going to talk about two specific cases, the work that we're doing on HIV and stroke. And then we're also going to talk a little bit about the work that we've been doing on behavioral assessment of at-risk infants. I feel like these two works will highlight kind of the different spectrum of where we're kind of thinking and the intersection between our use of technology and our use of it to probe disability in terms of motor function, but also disability in terms of neurological or cognitive impairments due to a variety of neurological diseases. So from a rationale point of view, we recognize that, okay, there's communicable diseases, there are non-communicable diseases. There are lots of stuff happening in the population that is around the issue of health. High blood pressure leading to stroke, HIV leading to dementia, and also a lot of strokes. Neonatal nutrition and issues leading to premature births, cerebral palsy, autism, etc. So we have this growing number of people that are living and working with neurological issues as a result of a variety of things happening. But as this population grows, what we're finding is, and I think this is not just in the United States, but it's across the world, there's a shortage of the experts who are able to care and understand the special needs of those with disability, and not just their motor needs, but their cognitive needs, their participation needs, just you name it. So there is this growing gap between those who can take care of those with disabilities, and this gap leads to a crisis in healthcare on many ways. And of course, because I'm an engineer, I think that technology can help bridge the gap. And I'm not saying that technology is the only way. I think there's lots of other solutions that we can think to do and apply. But I want to talk about how we've used technology to support the leveraging of the shortage of clinicians to support this population that's growing. So the first types of technology that I've been interested in using are I'll call therapy robots. And this area was something that actually I would say about 20 or 30 years ago began, where we started looking at the use of high-tech, smarter systems to support neurological recovery after stroke and cerebral palsy. And the premise behind using these technologies, and you see some of the figures here, is that we would want to be able to automate and deliver aspects of therapy and into the arm, the leg, or the joint, and this idea of repetitive motion and movement, and we wanting to engage persons in the act of doing rehab in order to drive neuroplasticity, connecting brain function and movement to what's happening on the outside in terms of the movement of their arm. We also wanted to be able to assess the level of function of the person with disability, with the idea that if we can intervene, how can we measure change? How can we understand the relationship between plasticity and what they're doing? And then, of course, the development of these systems, not just for our engineering inquiry, but that they're actually making a difference in terms of reducing motor impairment and motor function. So many of these systems typically are very, very expensive, and they're in the lab and in inpatient hospitals and supervised settings. The other category of robots and systems that we're interested in, and at least I'm interested in working with, are assistive technology and assistive robots. And the idea behind these robots are often kind of maybe they're social robots that we'll call them, or they're wheelchair type robotic systems, or they're delivery systems and humanoid type systems to support the replacement of functional activities for people with disability, replacement of a limb, or just being able to support what we call activities of daily living. And this was one of my favorite pictures of a Manus robot. And what you're missing is that there's another gentleman over here with high-level spinal cord injury, and the robots are being programmed to allow them to drink a beer, just like a classic American pastime, right? In fact, they were in the Netherlands, so it wasn't just classically American. So the idea then is, how could we use these two types of systems? So critically, my team is looking at neuroscience and rehabilitation robotics together and trying to use these principles to effect change and to understand a bit about disability after stroke, cerebral palsy, neurological brain injury. So we have 3 different areas, and our goal is how do we look at affordable robotic issues, neurorehabilitation, and the use of mobile and therapeutic robots for assistance. One of the things I like to do is to step back and look at human-human interaction, observe that. And for me, the human-human interaction that I'm most often observing are therapists interacting with patients and understanding how they elicit the complex dance of rehabilitation. We're examining their movement, and from that we build kinematic models. We're in examining how they interact force-wise, and from that we build haptic models. And then we also want to examine the behavioral dynamics, where we then build intent and understand then how do these 3 things together help us develop human-robot interactions. So these are examples of activities that we study, and then we code them. And then what we try to do is look at the state base or state space, or I would say system response interactions that are happening. From examining these issues, we actually identify 3 different roles that we see: therapist as demonstrator, therapist as helper, therapist as observer. And we then look and see how robots can support these particular roles, and how do you transition from one role to the other. So examples of therapists as robots already, in terms of mapping the activities of a therapist to a robot, can be done in a variety of ways. The helper role is one role where the robot's constantly in contact, demonstrator, observer, and then transitioning between the 2. This is one of our earlier systems where we applied to stroke, people with stroke, where our goal was to program the robot to support the movement and of the impaired arm for activity of daily living type tasks. So in this way, we've intervened with this robot. We've also collected MRI type data on how people were changing as a result of 12 weeks, 1-hour sessions, 3 times a week with this particular system. That's an example of a helper role. Another concept that we've been working on,
a remotely controlled robot.
Let me stop. Is this idea of the demonstrator observer role, robots that can be used remotely. One of my labs really interested in affordability. I can build a system that maybe 5,000 or so, place it within, co-locate it with the patient, but then the expert clinician is somewhere else. A big question here is, how do I translate movement and the activity that people are doing motor-wise, their responses to inquiries that the robot might be interrogating? How do then I use that to perceive their diagnostic, or to perceive and diagnose impairment, to perceive and diagnose where they are in terms of their therapy, their functional level, et cetera. So that one of my PhD students is kind of looking at developing those types of systems. We've also looked at more complex humanoid robots and try to ask ourselves, what type of behaviors and exercise that we can motivate patients to do. In this case, it was elder patients, and my colleague were working at programming these robots to interact with these patients. And the questions that we're asking is, what type of information do we get, and how can we drive motor recovery? So that just gives you a little bit of background. So you look at the diversity of things that we do. Recently, we started thinking about, well, how do we effectively use robots to help in a specific issue? So we wanted to look at stroke, and we also wanted to look at HIV. And this is the work of one of my PhD students. Just so I think this is a neuro group, but I'm not going to make an assumption that everyone's familiar with stroke. So one of the key things is to understand that stroke is the leading cause of adult disability. In the US, lots of incidences of stroke, almost more than 4 million people. But this is an issue that's a worldwide problem. 80% of new stroke survivors are in low and middle income countries. So this is recognizing that stroke is a unifying issue in rehab, that the work that we do can be applied universally. 75% of stroke survivors will have a motor impairment. Less than 10% will experience full recovery. The use of robot-assisted therapy has been really active within the stroke population in terms of looking at robots being able to cause, and let me present this graph. On the x-axis is sequelae after stroke, with the acute phase, 3 months within, 6 months, 1 year, 2 years, 3 year. And then this, if we put on the y-axis recovery of the upper extremity and the ability to do coordinated movement, muscle strength, things like that. And this Fuglemeyer is a clinical scale that we use to assess motor impairment. If someone is cognitively sound and they don't have any cognitive impairment, we find that the blue is like a typical recovery curve. People will recover, maybe not to their maximum functioning, but they will recover, and then they kind of plateau a bit. The use of robot-assisted therapy has shown us that if we use it early in the process of rehabilitation, we can drive plasticity even a little bit more, and we see better recovery of function. If we use it in the chronic period, we can also actually cause some plastic changes to the brain. Use-dependent reorganization is the term that's often used, and cause some bumping up of functional outcomes even late after people traditionally say that people can't recover after stroke. But what's true is that if someone has a cognitive impairment, in addition to their motor issue, we find that there's a big gap in functional outcomes. And so this is actually one of the things that I had my student trying to think about, is this issue of, can this robotic technology, can we use it to support those with both motor and functional issues? This led us to think about HIV. I have a collaboration in Botswana, which is not very far from where from South Africa, and they're in Gaborone. And our collaborators there, we were seeing HIV. There's a huge issue with HIV, but we were looking at the fact that HIV, the population there had HIV-associated neurocognitive disorder, and that often results in this mix of motor and cognitive challenges. And one of the things that we also saw, that there is beginning to be a lot more literature that says more and more people with HIV as they age, and this is from the US perspective, we're thinking about, well, they're aging, and that more of them are actually at risk for stroke. And then there's new data that shows that HIV populations are 1.5 times more likely to have a stroke. And there's evidence that HIV might be a risk factor for stroke. So we've done a lot of work in stroke rehab. And so this, and our partners in Botswana, we started asking, can the work that we've done in robot-assisted therapy for stroke be applied and useful in understanding issues in HIV, as well as those that present with both HIV and stroke? So that's kind of how we got into this area. So as we said, we've been here applying our rehab robots to interrogating and understanding disability and driving plasticity issues, stroke. And then we started seeing this relationship because we were working in Botswana. So then we started asking ourselves, can robots be a part of this dynamic as well? So the research goal that I had my students been working on is thinking about, how do we quantify in an affordable way, because we were thinking about Botswana being a middle income country, recognizing that there are challenges to this gap in access. How do we move away from the very expensive robot systems, create affordable systems. But in addition, how do we use these affordable systems to define metrics and robot-based measures that can allow us to quantify motor and cognitive disability, and maybe stratify this population into areas where those who need more therapy, those who need more motor therapy, or those who need more cognitive therapy. So this work actually was done in the US on a US-based HIV and stroke population. And our goal actually is hopefully in the spring with, COVID-19 and those types of things, that my student is able to get to Botswana and do this work on an HIV and a stroke population in Botswana. But as a way of studying the issue, we recruited patients with HIV who were on average 56 years old, and patients with HIV and stroke who also were about the same age match. And the overall population with HIV was about 56 years old. And we had a pretty good mix of gender. And in the US, there's a lot more persons of color, brown and Black and brown people who are presenting with HIV. So our population was a large segment of our population are Black. So what's our process? Our question is, can our robot-based metrics give us insight into cognitive function and motor function? We collected a battery of standard scales or clinical metrics: the Montreal Cognitive Assessment, the International HIV Dementia Scale, the Color Trails 1 and 2, and digital signal coding. These metrics are looking for a variety of issues in the cognitive domain. It's looking for visual spatial challenges. We're looking for working memory issues. And then we also collect a variety of motor and cognitive clinical metrics, like the standard Fugl-Meyer one that was primarily for people with stroke. But we also collected the box and block, which is a measure of looking at reach and grasp of gross motor function. We looked at grip strength, and grooved pegboard is a measure of fine motor function. So we wanted then to confront these clinical scales with the activity that we were doing with the robot to see if we can use our robotic methods to understand more about disability. This is the first robotic task that people had to do. It was a preview tracking task. You can see the robot in the background. I'll stop and talk a little bit about the robot. The robot is a 1 degree of freedom. There is a actuator, a motor within the system. There is a force sensor on the handle that allows us to measure interactive forces with the handle. We program the robot to able to provide assistance or not. In this case, we're not providing the assistance. We're measuring the forces, and then we're also measuring the position of the robot as this person do this task. In this particular task, we ask the person to stay within the square and to follow and track this trajectory. For that, we're measuring their performance error, the difference between the target tracking and what they did. We also collect velocity, acceleration, smoothness, total distance travel. Here's a figure that shows a little bit of an example of what 2 different patients could do on this particular task. In the dark blue is the HIV subject, and you can see the dash lines are the desired trajectory. And you can see the HIV subject was quite impaired and wasn't able to do as good a job tracking the desired trajectory as the other patient, who was less impaired and was able to do a pretty good job tracking, i.e. more accurate one patient versus the other. The other task was actually very simple. Typically, to assess and probe cognitive ability in terms of working memory, people use this end-back task, which is usually kind of cards, you're putting it out, and zero back means that if I tell you every time you see the number 2, you need to tell us, right? One back says, if I'm asking you to look for the number, you're going to tell me, you're going to tap if you saw that number the one time before, and then 2 back if you saw that number twice before. So what we did to make this robot based is we basically said, we're going to now measure the response time. Usually people just measure the score. Did you get it right? Did you get it wrong? Well, we wanted to quantify that. So what we did was added a button to the task to measure how long did it take people to react and to get it right or wrong, and also measure the type of errors that were making the reaction time. So this is an example of a group of persons with HIV and HIV stroke versus the healthy group in blue. And what we can see is when you look at zero back in terms of the score, people looked very similar. When you look at the reaction time, though, you begin to see that the reaction time variable was a much more sensitive than the healthy population had shorter reaction times than the persons with HIV and stroke. So it tells us that just adding the objective measure of reaction time and speed of information processing already gave us some additional information. Then one back, you see relatively the same, no real significant difference. And then in the 2 back, where the cognitive load on this task got a lot more difficult, we begin to see the separation from the healthy population, those with HIV and stroke. And then we see increase in their reaction time. So the metrics that we were using and we're hoping to use as feature or regression in a multi-regression algorithm could be reaction time and score. The third task that we built and deployed was this task that had, what we argue, a lot of almost equal contributions of cognitive and motor. The task was reminiscent of a Corsi task that's often done in cognitive assessment, and the spatial span task. You can see the video here where the user is first shown a sequence, and then they have to duplicate the sequence by moving the robot over the tiles. And the way we kind of perturb them is we might give you the sequence length increases over time of how many you have to remember over time and how much movement you have to perform over time. So we begin to separate those that the cognitive load issue and the motor issue begins to be seen in their performance in terms of the average sequence length that they were able to do well versus, for example, the correct response rate. We also calculate smoothness and velocity. Here's an example of someone that's more impaired, only able to do up to a 3 sequence lengths. And how we probe that is we actually do adaptive. So if you get it wrong, we take you down a level. If you get it right, you go up a level until we figure out where actually is your ability. And so you can see the separation between someone with higher functioning and someone with lower functioning. So what that has been able to do is, so the second thing that we're trying to do is stratify our population and figure out ways that we could stratify this population in terms of their motor function and their cognitive function. Let me present this task. So this figure on this axis, if we look at these on this axis here, is the difference between those that have higher function, low cognitive impairment, and those that are more cognitively impaired. On this axis here is the difference between those that are higher, they have more motor impairment, and those that have low motor impairment. What's important to note is that the people in this upper corner will be closer to healthy, will be people that have probably higher quality of life, and are people that may not need as much rehabilitation and therapy. In this lower corner are, we'd say, the more severe. So clinical assessments, like, for example, the box and block for gross motor function and the MoCA for cognition, we use that to separate our group into these particular quadrants. So the question we ask is, can our metrics, the robot metrics that we just collected, can we develop predictors and ability to automatically put people in these particular quadrants based on their performance? The first thing, though, is, can our metrics predict motor measures, and can our metric predict cognitive measure? And if we can do that using our robot metric, we envision, here's this low-cost system. It can, one, do therapy, but two, we can have a stroke survivor or someone with HIV sit at the robot, perform these 3 tasks. We collect the data and we immediately know where this person is in terms of functional and performance. And with that, we can then prescribe therapy. So what you see is that, for example, just quickly, in the NBAC task, we see the ability to discriminate against the healthier population, the one that's low impaired, and those that are higher impaired. We have trouble with the middle group, and we expected that. In the trajectory tracking task, we see the ability to also distinguish between the more severe group and the ones that less. And we also see that the low cog, high mod, high motor function, that there's some issues here with this particular group. The challenge is in separating the activity and the impairment amongst the inner group. And then we see the spatial span task actually had the best ability. The task that had both cognitive and motor elements had actually the best ability to separate out the people with that are more healthy from those that are moderately healthy and those that are severe. That actually was quite promising. Quickly, just for the sake of time, we were able to then show that based on that we were able to predict using, for example, the spatial span, mean sequence length, and performance, that we could predict cognitive scores, and that we also could predict motor functional scores using a combination of the sequence length, the cognitive motor task, and the tracking task. This actually was very encouraging because it realized that, one, we had some powerful things with a simple, an affordable robotic type system. We can now say we can assess cognitive and motor function, but we may then also be able to intervene, because with that robot, we can also do force feedback and challenging activities that could hopefully perturb motor and functional activity. So this is the grid. If you say the higher functional, the more severe group over here, robot assisted therapy, really good at this area, not much going on over here, and primarily cognitive here. So what we then realize is our ability to categorize people using these simple metrics then maybe open up the opportunity for more effective neurorehabilitation strategies for people with both motor and cog. Right? So so my next study is kind of thinking about, again, the use of very interesting and novel metrics and technology to try to now probe infants. So I just talked about older people with HIV and stroke, and now I want to talk about at-risk infants and how we've also started using technologies to probe that. And these, again, as affordable technologies, that's one of our motto. So Just a little bit background, 50 million premature births each year. 5 to 10% of people, of these kids probably will develop a developmental disorder. Cerebral palsy is probably the primary one that people think about. And the prevalence is 2.11 per 1,000 live births. We think it's higher in low and middle income countries. We know that early detection is crucial to maximize brain plasticity. And we also know that there are methods and clinical methods that are out there that people are using to try to detect whether a kid is at high, medium, or low risk, but they're often quite qualitative, quite expensive in terms of training. They're insensitive to small, delays and really early development. And they're not also able to be used as well in the wild. And so that was kind of one of our ideas for how we wanted to use technology. So our first pass at this was this development of a play and neurodevelopment assessment gym. We wanted it to be low cost. We wanted to think through interesting toys, and this was our first attempt at developing smart mechatronic toys that could be used to probe voluntary action. On the base here is a force sensing plate for us to be able to detect center of pressure movement from the baby. And on the frame is our cameras that allow us to collect visual data about what's going on. The toys were not just designed willy-nilly. The first two toys were kind of thinking about reach and grasp, and then we had a kick toy. The toys were all developed in the lab, looking at measuring grasping using a pressure transducer, for example. We have accelerometers in the toy to give us information about how the toy was touched, kicked, interacted with, as well as providing LED and sound for feedback to try to encourage the baby to interact with the toy. This is kind of an example of what we get from the mat, the data. So as the baby is laying on the mat, we're collecting center of pressure, almost the reaction forces that the baby is putting on the mat. And this, we're hoping, adds possibly an additional feature for allowing us to understand at risk, low risk, or high risk. So our research goal was to identify metrics that were able to distinguish the infant risk and be able to qualify, is this baby a typical developing baby, or is this baby going to need to get intervention now? We wanted to first look at the condition where the babies were playing alone, and then we wanted to look at the conditions where they were interacting with toy. And our goal was to use machine learning techniques to automate and stratify these babies. So we used a big data approach here, where we curated a database of normative infants, confronting that with our clinical infants, and then looking how we could compare and assess risk. So this team was a group that was also Dr. Cording. Many of you who did Neuromag Academy are familiar with his lab, and this was done in conjunction with his lab. How do we get the normative data? We essentially searched YouTube, we looked for keywords, we sorted through a bunch of videos to find videos that were the infants weren't occluded, they could move independently, they could, that they were actually, there and doing something for 6 seconds, at least 6 seconds. And we found a ton of videos. Some, of course, weren't useful, but others we found a lot of videos that we could use, and where we had kind of babies doing and moving on their own. Then in terms of the clinical data set, we worked with the Children's Hospital of Philadelphia, and we recruited the clinical population from the Children's Hospital. And these were babies that were either noted to be premature or having some type of issue, and they might have been in the NICU, the neonatal infant clinical unit. So this is an example of the two types of data that we got visually. So first, This is a infant playing by himself on the mat. And essentially, this is what we call the no toy condition. And then this is the condition where we suspend the toy above the infant and the infant is interacting with the toy voluntarily. We are not directing the infant in any way, but we're using the sound and feedback to try to entice the infant to do voluntary interaction type tasks, reaching and grasping, kicking, whatever they want to do with the toy. We're going to focus on the no toy condition. So in the end, we ended up with 103 YouTube videos and 85 where we were able to have the clinicians assess the age. We ended up with 19 infants that were each assessed with this Bailey infant neurodevelopmental screener that looked at, was a quick screen for neuromotor risk. That screen classified them into 5 low risk, 9 moderate, and 5 high risk. So the question then is, with this label, could we develop a machine learning technique that would be able to accurately classify the baby? So this is our algorithm pipeline. We have the 2 sets of data. The videos were annotated, they adapted in OpenPose. We fit the pose to the video, we extracted the movements and features that we wanted to look at, and then we used the Bayes naive surprise metric to look at clinical judgment, algorithm to look at clinical judgment. So just to give you a little bit more detail into the process, we use the computer video-based pose estimation to extract infant pose. And the OpenPose is an algorithm that was developed by Carnegie Mellon University. It's probably very, very popular in terms of extracting movement information from 2D videos. They use convolutional neural networks, heat map, and part affinity fields to be able to then come up with these skeletal models of a person and a patient interacting. What's interesting was initially OpenPose was developed mainly for adults, and it was trained on data sets that really didn't have any infants in it. So when we first did it, it was really terrible in terms of recognizing the infant movement. And so one of the things we had to do is retrain the network. And we retrained it by providing the 10 seconds of information, and we had to label using VATIC the movement. Then we had to essentially ended up with 8,000 frames in the training set, 1,000 in the validation set, and we're able to improve its ability to detect the babies. So this is an example of OpenPose, the algorithm overlaid on one of the videos that we have with the babies. Cleaning up the raw data now, once we got them from the pose data, removed outliers, did a bit of smoothing, dealt with the fact that with the YouTube data, we didn't know where, and the focal, field of view with the camera. So we had to normalize the data with the trunk of the infant. And so that we then just focused on looking at the upper extremity movement and the leg movements for the infant. It's an example of the kinematic features, all the ones that we pulled. These are type of kind of information that we got out of the pose when we looked at left ankle, right wrist, just to say. So we were looking at the wrist here and the ankle here, as these were the end effectors of the baby. And so we wanted to look at overall movement for those as kind of key features of what the leg and arms were doing. And then, so this is kind of like the information in the position, the Y coordinate distance that came. But we also looked at angle, the speed, velocity, acceleration, left, right, variety of these features. And these were pre-registered so that we would comply with kind of, good machine learning practices. This is an example of some of the metrics that we were pulling off, and you can see the gray dots are the YouTube infants that represent our healthy population. And it's just important to note that we did, from a healthy population, we had our clinicians examine all of those YouTube videos, and if they even thought that one of the babies were impaired, that video was removed. And remember, we use clinicians that were very well trained in detecting anomaly in baby movement. And you can see in the colored dots, these are the low risk infants are in green, moderate risks are in blue, and high risk in red. And you can see that there might be some trending or some kind of separating of the low risk the healthy infants from the infants at risk. But it's kind of hard to say with just looking at all these different features, which is why, using machine learning techniques are really powerful. And then as we get more and more data, we hope that we are able to do these types of classification even better. So the naive Bayesian surprise metric was used and applied to the data set, and essentially showed that we were able to, with significant difference, separate out the high and the high risk group from the YouTube babies. The healthier babies weren't as successful, though, with the low and the moderate risk. And this is not surprising in one sense. This is the same issue that they have when they do subjective measures. However, we believe that maybe we just need, we think it's still possible. What we believe, though, is that we need additional data, and we might also need to tune our features in order to be able to identify which to be able to separate out this middle group a little bit more. In fact, we have a grant to collect 1,200 of these data sets for babies in a variety of risk categories. And then our goal then is to confront that larger data set with our algorithms, and maybe improve the algorithms at their ability to do the classification. So clearly we believe that we can classify impairment. We also know that we need more. We need to understand this issue more, and what are the features that need to go in. And then our goal then is, can we do this with the toy data? So initially, just to give you a sensitivity to the type of stuff that comes out of the toy data, is if we're looking for different types of interaction, like left, right, touch, grasp, kick, all these variety of things that the baby might do. Here's some examples. The baby is gazing at the toy, and each toy in different ways. This is a toy that was suspended at the feet, the toy that was suspended at the level. You can appreciate the obstruction that might be going on in terms of the type of data that we got due to our camera angles. It's an example of hand engagement, and it differs according to the toy. This is an example of kicking, using their legs to do reaching with the legs. Younger babies, we know, tend to do reaching with their feet before they discover their hands. So we see examples of that. And we also look at interactions that happened not on purpose, that were quite involuntary. I mean, how are we able to then automatically code for that? We first asked the student to try to identify if there are any real trends in looking at differences between typical and atypical kid in a very brute force qualitative analysis methods. And this is just an example. For one of the toys, we're able to find, and looking at total interaction time, that the typically developing kids had much higher interactions with the toy than much higher voluntary interaction with the toy than the atypically developing kid. And when they break this down by toy and look, and in fact, we're looking at the data now, realizing that there might be features here that in the toy and the voluntary interaction with toy that we should be being able to pick out. And the question is, how can we do that using machine learning techniques? So a lot of questions that we're asking ourselves is, do we need to add more cameras so that we can have better unobstructed views of the infant and the toy? So these are the things that we're thinking about now. And our opportunity is to collect, better data, in fact, we think. So first thing we did is simplify our process. Now we're down to one mechatronic toy that we developed. It's as similar to the ones before. IMUs, pressure sensors to be able to detect baby holding on and squeezing the leg. There's surface sensors in the face for touch. There is LED feedback in the ear. If the baby squeezes the ear, it gets feedback, and there are a variety of things. So this is a very sophisticated mechatronic toy that we've developed in the lab. And then now we also are moving to make this whole system more portable. This is an example of like our current iteration. And notice that we also are putting a lot more video cameras pointing down to see if we can get the right angle so that we can be able to automatically apply ML techniques as well to the baby's interaction with the toy, and not just understanding from their interaction by themselves. I'm going to stop there. Thank you guys for your time. I think I went over a little bit, but I'm always excited about talking about these issues and acknowledge that, of course, there's a large team involved, lots of funding to be able to do that. But what I tried to do was present two types of technologies that have a relationship, that are affordable, that I'm hoping could be used in both high and low resource settings, that could be used to interrogate behaviors that are, an impairment after brain injury. So I'll stop there. Thank you for your time, and I'll take questions.
Thank you so much. That was really, really great. I really enjoyed it. We do have quite a few questions tonight. Our first question is from MN, who is unfortunately in a noisy setting, so I will be asking the question. So with the Botswana setting in mind, how do you intend to ensure community buy-in? Are these communities eager or accepting of these technologies? And how much support will there be for these patients once the technologies have been installed? So this is technical support or training for the staff.
Great question. So the first study, we actually have a grant from the Center for AIDS Research, and the University of Pennsylvania actually have an active partnership with the University of Botswana. And they've already formed this partnership, and they've already been doing a lot of work in Botswana around HIV and around understanding rehabilitation and stroke. What we've been trying to do, in fact, we're right in the beginning. We just got IRB approval, just hired our first Botswana person to help do research. And the question you asked about buy-in, it's we have on the ground colleagues that are really excited already about this work that we're doing, and colleagues at the University of Botswana, at the hospital, Princess Marina Hospital. And now the work that we have to do next, in fact, is we're trying to understand the issues around rehabilitation there. And then I think it's hard to tell you, that is there buy-in from the patient. I can say from the United States, we know that that patients are excited. They are eager to find things that will help improve their function. The patients in Botswana may not be used to this type of technology. So I am hoping, that they would have the same buy-in. But one of the things that we're trying to do is ask. is expose the clinicians to the research. We want to do capacity training as well. We want to teach clinicians about rehabilitation, about this type of technology, and then we want to expose patients to it, and then that's a part of the research. We have to collect that data. I don't have any reason to think that they'll reject the technology, and one of our philosophies is that these technologies are bridging the gap, as in they're not here to take your job, they're here to supplement the fact that you don't have enough clinicians to treat your population. And so therefore, how can these robots be used wisely by you to help? So I'll get back with you in a year maybe to see, how they truly appreciated what we do. But I'm hoping, based on the feedback from colleagues who are on the ground in Botswana and who are themselves, seeing the possibility, I hope that they'll receive it well.
Great. I'm going to skip ahead to another question. I think I'm more thinking of the South African context and the Botswana context in asking this question, but what sort of measures are there in place to ensure security of these? I mean, they are designed for low resource settings, but they still cost something. And then also the demands on the existing power grids. What sort of measures are being taken there?
Good question. And so these are questions that we grapple with all the time. That was one reason for choosing a 1 degree of freedom robot system as opposed to more complex type robot systems. One of the things that we do in terms of, so you have a lot of questions in there, but I'm going to try to hit. So in terms of cost, one of our philosophies in development is using the World Health Organization idea of what is a cost-effective strategy in terms of intervention strategy for middle and low income countries. And their strategy says, look at the gross domestic product per capita and use that as a way of thinking about cost. So one of the things they say, what's highly, highly effective is what's cost effective is if an intervention or a product that's between 1 and 3 times the gross domestic product of that country. So we've then chosen to say, okay, can we build this technology for $1,000, $2,000 US, which is in this case 20,000 pula, or I don't know, in South African dollars, how much is that? How much is that?
Roughly the same, maybe, but yeah.
So roughly about the same. It's still expensive, but it's not $100,000 that a lot of the other systems might cost in the United States. That's the first thing. The second thing is working with local engineers to see if we can even drive that cost down even more, right? Because one of the assumptions that we make is when we're here in the United States, we're pulling from what we have and we go, this is low cost. We take it to Botswana and they go, not quite. So then we collaborate with engineers and say, how can we make this cheaper? How can we leverage what's in Botswana or what's in South Africa to make this even cheaper and more scalable within countries? So we deal with that as well. So that's a kind of I apologize for my dog in the background.
It's okay.
So this is I think a part of what our philosophy is. How do we re-engineer it for local context so it's appropriate and affordable? And we've been working in Mexico, we've been working in Costa Rica, I have colleagues on the ground in these different places and thinking, what's our philosophy around all of this? It's collaboration, but the problems on the ground for these stroke survivors and people with HIV or people with cerebral palsy are very similar from a rehab standpoint. The access issue is what is at issue here. And so I love social justice. From that standpoint, I go, why should, if I live in South Africa, my functional outcomes not be up to par, when as the same person living in the US? So these are questions that we grapple with. So how can we do that? How can technology offer that opportunity? And how can we build the capacity research-wise. And I know they're there. I mean, there are people on the ground doing really great work. It's like, how do we partner to bring some of this stuff or technology into the setting and to see how we can get it to work?
That's great. Stanislas is from Zimbabwe, and he's asked a question in the comments. Would it be possible for him to send you an email or via us, or?
Sure.
Cool.
Absolutely.
Cool. Well, Julianne, would you mind posting the email address in the comments then? Thanks.
Yeah,
I'm going to continue with the questions then. So the next question is from Amy Dolman, who's asking, do you find any difference in ability to use as well as benefit from the robotics between patients who are more familiar with technologies versus those who aren't? For example, patients from more rural, low-resource settings. This is similar to the concept of test wiseness, familiarity with testing equipment and environment in cognitive assessment.
So usually people ask that question about older versus younger. So I'm going to use that as the metaphor for urban versus rural, or, not tech savvy versus, more tech savvy. Because usually people argue that elder people who are less tech savvy will not appreciate the use of the technology. So I'm going to use that as the framework for my response. I believe that, at least from what we've seen, is even though people are more tech naive, one of the things that we try to do is say, think of this as a tool. It's a smart tool, right? And I like to even give this example, and then when we explain it in those contexts, I think most people have been willing to use the robot systems and actually been excited about their ability to use it and to hopefully get benefit from it. And we explained that it's like the treadmill. Before there was a treadmill, when people tried to imagine the treadmill, they couldn't even imagine the treadmill. But now everyone uses the treadmill, and the treadmill seems, you can work out on the treadmill, and you see the treadmill as just another tool that is now affording you the ability to walk outside when it's raining, to exercise and things like that. So I think a part of the challenge here is we see people wanting to use these robot systems. They're actually elder people who are accepting of the systems, even though they're not tech savvy. And we believe that people, when we were in Mexico, we did some work in exposure in Jamaica, people are excited. They're like, whoa, something that can actually help my patients, or something that can actually help me. Now, the challenge is getting it in the ground and then collecting enough data on people using it to then definitively answer that question. So one is, I don't believe that there should be any reason why people will reject just because. However, we do need to collect that data.
Great. Next up, we have Guillaume. Guillaume, do you mind just giving a quick introduction to yourself before asking your questions, just who you are and where you're from?
Yeah. Hi. First of all, thank you, Professor Johnson, for this amazing talk. It was a really interesting one. I enjoyed it thoroughly. I am from the University of Stellenbosch, busy doing my master's in biomedical engineering with a focus on developmental assessment with regard to tablet tests and gamified assessment and analysis of that, say, the interaction with the tablet.
Yeah.
So my question is, with regard to developmental assessment, have you and your team looked at smart devices such as tablets and apps and the children's interactions with the devices and how they perform on these apps to help determine and or classify possible neuromotor risk and or cognitive deficiencies or such like that?
Great question, and that's a great, a really good way to think about the use of mobile health technologies and how they can be a part of that assessment process. So, excellent idea. We have not specifically done a lot of work in mobile health and looking at iPad and the use of the interaction between those types of digital media. We have used exergaming. We have tied our robot systems to gaming type systems to use that interaction to assess impairment as well. So we have done that part. We just haven't used it necessarily on kind of the iPad or the Android or through the phone. I think it's possible. I know that it's been a technique that has been used by some colleagues, mainly in the computer science world, like in terms of that interaction, and it's been effective. Like I can imagine that there is a use for one of these, a colleague in Botswana was talking about neurocognitive assessments done through the iPad or Android in terms of brain games and things like that. So I see a use for it. Absolutely. We haven't done as much with that. We're open to it, but I think we've partnered with groups that use that medium more than we do. And one of our thoughts is tying our robots that need to provide assistive and movement to these types of mobile devices. I'm open to that. I think that's not a bad idea. Hopefully that answered your question.
Yes, that does. Thank you so much.
Great. Great. While Carly comes online, I'm going to ask the last question in the list. So in terms of screening at birth, just to give a little context behind the question, a lot of children get discharged after 3 days, especially ones at high-risk birth. And there are measures in place to help mothers identify developmental milestones, but it doesn't always happen. So these high-risk babies are born, they go home, and then the mom only realizes after a year there's a problem because the kid isn't sitting. Do you have any ideas or things in place for at-birth screening?
Excellent question. I think this is a huge issue. It's a huge issue. It also happens in the US, and it's something that's actually one reason why we started this project, is thinking about automated assessment. And our project right now, we're focused on 1 month to 6 months. Like if we can figure stuff out between this delicate population, in that time, how can we do it? So one of the things we've been exploring is video. So there's this gross motor assessment measure, which is the scale that clinicians now use. They take videos of babies, sometimes 2 weeks old, close to that 1 month old, and then they take them at 3 months old. And they go through a very long training process to evaluate the baby's risk. That actually has a really good sensitivity and specificity, but it requires a lot of training. So the idea then is, if almost everyone everywhere now have cameras with a single, with the video, and people collect data on their infants all the time. So what we're thinking is, if you are using your smartphone and you're just collecting this video data, of your baby playing, is there a way that we could automate that process where that information goes through our algorithm, and then we can provide that mother, that caregiver with data instantly that says, maybe you should pay attention to this, or your baby is not attending to the cue on that side, or they're in this phase, or they're at moderate risk or low risk, so maybe need to pay attention. That's our dream, actually. So is there something that exists now? There is a technique that the therapists here in the US, they swear by. They say this technique is actually really good, but it requires a lot of training to do, and a lot of time. However, we're saying, is there something that could be done quicker? And that's actually what our research is on. This is something that we could put in the hands of mothers and of caregivers and of clinicians to monitor and to look at that development issue and then be able to flag it way before 12 years, like 12 months old, when it's almost too late. Because we know actually a colleague who's a therapist here in the US with the Children's Hospital of Philadelphia did some work recently where she was showing that if you don't intervene between 0 and 18 months to almost 24 months, that it's interventions that happen between 0 and 24 months that make a difference in the lifetime. And so that's critical. So like if we don't catch it between those two markers, we almost have defined the trajectory of the child for the rest of their life. So I don't think there's anything out there quite there yet. So I think this is an active topic, and anyone who's interested in that, I think it's a really important one. But I do think that ML and machine learning and those types of automated techniques that we're trying to also, I think there's a role for that.
Great, thank you. I'm going to hand over to Carly now. If you don't mind just giving a quick introduction before launching into your question.
Can you hear me?
Yeah.
Okay, perfect. Okay, so I'm Carly. I'm actually Julianne's sister. I'm a final year medical student at Stellenbosch. So I actually have a stroke question. You sort of answered my question, so I just tweaked it a bit. I wanted to know how the intervention that the robot provides differs between the acute setting and the, say, subacute or chronic setting, where the impairment is obviously very different.
Mm-hmm. Good question. So one of the key things that I feel like it can't be one size fit all. So one of the rationale for trying to spend all this time developing good assessments of motor and cognitive function is to be able to tune the robot's intervention so that it is different between the acute and the chronic phase. So in the acute phase, we know that there's a lot of spontaneous, rehabilitation happens, spontaneous neuroplasticity. And then there's also possibly the ability to tolerate less intensity, right? And we also know that there's increased inflammation. There might be this opportunity to, if the arm is not as active or as strong, the robot may need to do more work. It may need to still move the person through the movement, but the higher forces, the robot may need to be stiffer, may need to do more of the work than the patient. But just like in therapy, there's that space of flow, right? We need to get it so that the patient just does what they can and maybe a little bit more, and then the robot is not doing too much more. So as the patient gets better, the robot does less, the patient does more. So how do we constantly measure where you are and how you're functioning, your level of motor impairment, so that we tune the intervention to be appropriate to where that person is? So that's actually our philosophy with acute versus chronic. But the patient there could be a very high functioning patient in the acute stage and a low functioning patient in the chronic stage, right? So the issue is what is your current level of function? What are we trying to do? And how can we tune or measure and understand where you are so we give you the appropriate level of interaction that patient is needing in order to see recovery? Hopefully that answered your question.
It does, thank you.
You're welcome.
Great. Then our final question for this evening is actually about the model itself. So MN is asking about the surprise metric that was mentioned. If you could maybe elaborate on what you meant by surprise.
So the naive Bayesian surprise is kind of one of those classic ML techniques that we chose to use. And the reason why we ended up with this technique is because it's known to be a little bit forgiving in terms of the number of data points that we need. And it assumes a normal distribution of the population. It assumes that the features that we're trying to predict are independent. It is essentially trying to figure out what is the probability. So officially, it's estimating the log probability that the feature of one movement is within the normal distribution of the healthy population, right? So it's trying to say, what's the probability that this infant is within this normal distribution? So that's essentially what that methodology is trying to do. And it's a nice process because so where you have to have a lot of numbers is in your healthy population, because you have the norm. It's saying, do you have a normal distribution of that population? And then now with the 19 babies that we had, we're asking for each baby, how do you fit with this normal? It's almost like the Z, like if you're calculating the Z metric, how far are you away from the mean? It's like doing that, but on a kind of a larger scale. So that's it's just a mathematical technique that actually is quite useful for allowing you to not have to have 1,000 data points, but you could do this for the 19 data points that we have. We're comparing it to this normal distribution. That's why we ended up going there. What we hope, though, is we can maybe utilize other types of ML algorithms later when we have the data that we need. Because right now we didn't have the numbers that we needed to be able to do other types of methods. Hopefully that was helpful.
Yeah, that was a really good answer, I think. Thank you. So that wraps up our Q&A session. Before I hand over to Julianne, I'd just like to say a huge thank you. This work is really impressive and so relevant in the African context. So thank you for your time. And yeah, I think I'm going to hand over to
Julianne. Maybe in Botswana, given COVID, etc., I was supposed to come on my Fulbright 3 times actually in the next year. So I'm supposed to come in, I think February, March, sometime in the summer, and then sometime in the winter. So keep in touch. Maybe if I'm down there, I can see what you guys are doing and be able to form some stronger collaborations in South Africa as well.
Yeah, that's fantastic. Botswana is a beautiful country. So besides all the amazing work you're doing, it's going to be an amazing trip.
Hopefully. So there is someone asking, referring to smart devices. Yes. Guillaume was saying by mobile health smart base. Yeah. Any other issues or?
No, I think that's it. Your email was posted in the comments, so if there is anything else that you might get an influx of emails after this talk. I have a feeling they will be.
Guys. Thank you again. It was fun talking to your group, and I look forward to interacting with your group a lot more in the future. I love what you're doing. Can you put me on your email list so I can find out like when your next talk is coming up? I definitely think your area is relevant to what I'm doing, and love to maybe sit in on other talks myself, but on the other side as a guest.
Absolutely. I will add you to the mailing list. But anyone in the comments that would also like to be added, we do have a little button, but Prof. Johnson, don't worry, I'm going to add you straight after this talk.
Take care, guys. Thanks again. Bye-bye.
Perfect.
Bye.
So just as a final note on tonight's event, I'd just like to again also thank Prof. Johnson. So it was fascinating. And if you guys can all just show your appreciation by giving Prof. Johnson a virtual round of applause in the comments. And then thank you to all of you for attending. And like Siobhan said, we have a little button at the bottom of the screen. So just follow that link if you'd like to join our mailing list and find out about future events. then we will keep you posted on what's coming up. Then lastly, I'd also like to thank our sponsors, the Biomedical Engineering Research Group at Stellenbosch University. And with that, that is then another Nerd event done. So thank you, everyone, and good night. Bye.
Bye.
Bye.